So I prepared a few questions, but by all means feel free to expand or go in different directions if you think that's more appropriate. So from what I've seen, there appears to be some things that seems to be that can be shared between the Freescale and ARM architectures in terms of hardware tracing facilities. And I guess there are some other things that might be so different that really has to be architecture specific. Do you have some thought on what could easily be generic, and do you foresee that some things really need to have some kind of architecture specific extensions?
So, from what I know, from what I have seen in Freescale, each silicon vendor appears to be developing their own unique capabilities. And sometimes it is not possible simply to use off-the-shelf technology to support those unique features. And this is why, in those cases, oftentimes the silicon vendors end up providing their own debug solutions. By debug, I mean trace and performance analysis counters and so forth. So this is basically where we are with this. Now, you'll find that a lot of times these systems are designed in a very similar way. Years ago, I had to develop some tools that used that decoded ETM trace. So I did take a good look at the capabilities of that tracing solution versus what Freescale was providing at the time, and that was Nexus. And I can tell you that at least from a functional point of view, the two were very, very close. Of course, there were differences in terms of how they were implemented, some minor functionality differences, but otherwise they were fairly similar. So I think that the open source community could look into providing common ways of supporting different technologies from different vendors, for example.
Yes, I think where we have solutions in common are things like instruction trace, where every core from every architecture is basically doing the same thing. They are running through a series of instructions and tracing what the core is doing. And you can imagine that actually what you're seeing out of core side instruction trace or Nexus instruction trace is similar to what you'd see out of Plenary or any kind of software emulator. So the basic principles are the same. The only difference is the very low-level details of how it's set up and configured, and of course things like disassembling the instructions. So that's a kind of situation where we are in software tools where we have common concepts like object files, executables, images, and so on. And then each architecture will plug in its disassembler and its own set of relocation codes specific to that. And that's a solved problem in the software community. So I think certainly for core instruction trace, we ought to be heading towards that, where it's seen as a generic feature and it's simply enabled in a specific way. I think where we perhaps differentiate more is on tracing particular kinds of IP. So where we have particular types of interconnect or memory controller, there's much less standardization in how those are traced. And GPU trace is a very interesting one. I mean, we are continually sort of asked about, how do you find out what's going on inside a GPU? And this is becoming more relevant as people try and offload work onto GPUs. And even ordinary application programs start using things like OpenCL to push work onto the GPU. That's an interesting question of how Linux is going to deal with that, how we can get a sort of architecture neutral, GPU vendor neutral view of what's going on there. I don't really have an answer to that, but I'd love to see again a sort of architecture neutral solution to that. But I think that the default assumption should be that if there's an abstract concept that works across the architectures, let's embody that concept in a piece of software infrastructure and then try and differentiate or try and specialize only at the lower levels rather than gratuitously exposing that difference up to the end user so they have to work with different sets of tools, different interfaces, different architectures.
One thing I gather is that it goes beyond doing that per architecture. Even within an architecture, you want to talk to the GPU, you want to talk to various specific components. So it appears that in the end you'd have something like one driver per component, but then you might want to expose each of those components in a similar fashion to the end user.
Well, so, just picking up the conversation here midway, but for that, we envision that there will be a list of generic configurables and data available for each component. And just like an IP table module where you have a specific part of your IP table command line, you also have generic parts. So it's the same thing for a driver and how you configure it and how you expose it. So we intend to have specific parts that tool will hook up to, and also generic parts, or specific parts that specific modules will hook up to, and generic parts that will be guaranteed to be there in order to guarantee the proper working with the rest of the framework.
All right. Another question I had. So it's about the transports. I guess would it be seen as a kind of component, or I've seen there are various ways to export the data. You can write it to memory, keep it in smaller memory blocks, or use some external interface to export it. So how would you see that presented to the users?
I assume that you're referring to the decoded data. Is that correct? Or are you referring even to the binary data then?
So what I'm referring to is how to set up the communication channels so that the data gets exported in one specific way rather than another. So how is the I/O being configured? I'll come to the binary data format later.
Yeah, I think that this is a topic that is worth investigating. There are multiple trace data sources, and in the case of the 100 trace sources, you have seen in Al's presentation the three main ways that the data can be collected, right? One is the on-chip trace buffer, the other is the system's main memory, the DDR memory, and the third would be an external trace box. So is there some opportunity for doing some standardization at that level? Perhaps, yeah. But I guess we'll have to be in touch, at least among us, and see where we can find the common ground.
Yeah, I should say that the sketch of the system that I presented on my slide was a very, very simple one. We actually see people deploy much more complex systems where they have multiple trace buffers. They may be able to route one source to a dedicated buffer and another source to RAM. And this particularly makes sense where you've got things running at very different bit rates. So you might have STM coming out at a kilobit a second and instruction trace coming out at a gigabit a second. You don't want the instruction trace to come like a fire hose, wiping out all the STM software instrumentation trace, so you probably want to route those to different places. So you want to have the flexibility in the sort of the control over the topology to route those things to different places. I'm pretty confident that we have that flexibility in the framework that Mathieu is about to upstream. But yeah, exposing a way to let the user control that without exposing them to the full complexity of the hardware is difficult.
One idea there might be to design the generic kernel interface to have the full flexibility that you need for those use cases, but then not necessarily expect that the end user is going to interact directly with those interfaces. So you could have like a user space tool that would make the common case very easy, and but then leaves the flexibility to fine-tune and tweak as desired.
Yes, I would love to see that, where we have the sort of the lower levels as a really robust, flexible, heavy lifting component, and then you can build 100 different use case specific scripts on top of that. I really love the sort of D-trace approach where you have something that's absolutely rock solid, very versatile, and then you can just have everybody customize it. I think that's where we could get to with things like hardware trace.
Then the following question is about trace formats. So in the past year, I remember a discussion I had with some kernel developers where basically they were not very keen in having the kernel kind of export a kind of per architecture-specific trace format, for which the spec is not necessarily available easily or things like that. So some of them were saying that there should be a conversion in kernel before being presented to the user space. But how do you see that compared to overhead constraints and things like that? Perhaps we'll take an answer from the audience.
I fully agree with the idea, right? It would be cool if the kernel is spitting out everything in the common format. It's virtually impossible when it comes to hardware trace, and the reason is quite simple. So I just made some experiments. There will be another presentation about it tomorrow, I believe. So out of about a second of hardware trace, right, which you will get in the compressed format, you will get something like 50, maybe 80 megs of binary data of the highly compressed architecture-specific hardware data. If you then decompress it to a perf stream, okay, particularly if you decompress it into this in such a way that you will generate a set of accurate data by just multiplying samples. Well, I gave up when my systems started telling me that the disk space is low, and I've got a huge hard disk, right? So I wouldn't mind seeing decoders in the kernel at all for very simple cases when you actually just decode a part of the flight recorder decoder, for example, right? 10,000 instructions, the last 100,000 instructions, that's cool, but there must be a way of getting this raw data to user space for further analysis. So I don't mind, the idea of an internal decoder, that's cool. It could be even using loop, right? So you get the data out of the user space, but then the user space tool, in order to do the decoder, just ask a kernel to process it later on. Crazy idea, but it could work. But there must be a way of exporting this data in a raw format further on.
Plus, it doesn't scale. Like, it doesn't scale
Following what Paul was saying, it just doesn't scale with regards to decoders that we have. So engines decoding, right? We have ETM, we have PTMs, and we have ETM before. How many more do we have? That's just for ARM, right? How many for MIPS? How many for Intel? Having that in the kernel, in my opinion, or trying to submit that, in my opinion, is the best way to get your patches rejected.
I think, as Paul mentioned, we do have a issue where if we were to expand the trace to be like sort of a few bytes per instruction, we would massively inflate it to a point where it's totally unusable. But on the other hand, I think we can actually adopt a compression format that was more efficient than what's used by CoreSite. The CoreSite compression format is designed to be generated on the fly by a piece of logic that can be implemented with a reasonable amount of gates. It's possible to actually imagine compression formats that are more highly compressed by perhaps spotting longer range patterns. So I think the opportunity is there for somebody to come up with a generic trace compression format that could be used in something like CTF to trace very long sequences of instructions with a very high density in a way that was architecture neutral. And then it would then be just simply a matter of getting CoreSite or Nexus or Intel's process trace to be recoded to that format at some fairly early stage, not necessarily on the target, but at some point trace generation. And then the viewers and so on could deal with the generic format. And there's been various sort of academic work in trace compression, which people could build on.
Okay, so I guess you would advocate for a converter approach, but where the output format is as compressed as the format found in the system. Yeah, that might work. Sorry?
I was just saying that I will remain skeptical on that particular subject, on the generic compression for that, because it's academic work, so that's right.
Yeah. Let's wait until we see code.
Yeah, exactly.
I mean, another approach that I'm thinking about is a project like the Battle Trace converter and library project. So we are currently re-engineering so that it supports much better out-of-tree trace input and output plugins. So basically, we could use Battle Trace to read kind of architecture-specific trace formats as well as CTF. So this is something we could envision. So kind of not necessarily having to do the conversion phase to another format, but directly use the trace reader library on the native format. The last question I had, and please, I mean, I don't want to drive all the discussion here, so if you guys have questions, it's really time to ask. If not, I'm going to talk about timestamp correlation. Oh, yeah, we're done.
So this is maybe just a silly comment, but it sort of seems like, at least what I read is the reaction to the Intel packet trace patches, the existing maintainers seem to be willing to stick with we have no support for hardware trace option. And I wonder if that's partly because they're not hooked on instruction tracing. They're not hooked on the facilities that hardware trace provides. And I wonder if it was presented as a set of different alternatives, like here is in-kernel instruction tracing using software breakpoints, and that's really, really, really slow, but it'll work everywhere. And then here's the hardware support, which does the same thing, which maybe you agree to because it works everywhere, and it's a target-specific optimization. If somehow that would, I don't know, make things more of a gradual slope rather than a step function.
So this was the first reaction after the original Code Aurora patches were sent. There was a lot of comments regarding, can you just make it look like Ftrace or Lauric? So it would be very, very hard, but that's this is one of the ways that we could actually provide, instead of having a decoder and the universal format being exported to the user space. That's why I was so keen on having the decoder in the kernel as well, because then you could actually make, as I say, present this to the user as, let's say, just a trace, right? So just cut a file, it will decode the instruction and show you the last 2000 instruction, whatever is in the DP. So this is one of the possible approaches.
Other questions? So about timestamp correlation in that case. As you're certainly aware, things like the common trace format allow describing different clocks and relationship between the clocks, and then, well, you can put kind of correlation points so that basically if you get, let's say, your CPU to read some external clock value in its own notion of time and do that let's say periodically, you can basically have correlation points in your system. So as I understood, correlating hardware traces with what's happening at the system levels appears to be important to you. Is it pretty much just a question of extracting those clock values, and are there many clock domains in the system? Is it a single clock domain? I mean, how far do we have to go?
In the case of the architectures that I'm familiar with, the answer is yes, there are multiple clock domains. Those have asynchronous clocks running at different speeds. And on some of the systems that I have worked with, those clock speeds can also be variable. There were some processors that were running into some communication processors that, for power saving reasons, were varying their clock speed quite a bit. So the processor, just like for the x86 architecture, they were going faster or slower depending on what the application needs were. And unfortunately, that was also reflected in the timestamps that we were seeing in the trace data. So yes, the values were monotonically increasing, but the clock frequency had changed from time to time. So it was one more level of complexity. So yes, it's a non-trivial issue.
Yeah, I didn't go into detail in my presentation, but in core site we have essentially two different time bases. We have the cycle count that gets attached to instructions or to branches, but we have a separate global timestamp which is injected into the trace stream periodically. And that is always on, it's constant rate, it's essentially a kind of time base for the whole system. That's also used to timestamp STM messages, so that can be used to correlate trace around the system. And the trick really is to try and synchronize that with the kernel timestamp and the user timestamp, so the software timestamps. And there are various ways in which that can be done. So you can read the kernel timestamp and push it out as an STM message, and that gives you a correlation between the kernel timestamp and your core site global timestamp. Harold's got some patches that he's pushing up straight to synchronize kernel user space timestamps.
Yeah, but this was one of the reasons for my question previously, because as I say, the problem is quite close to my heart currently. But the thing is that when it comes to the typical solutions, so synchronization point, where the well-known timestamps from different domains, the processor trace, instruction trace, actually gives you some extra possibilities. Because in some cases you could try to do some crazy stuff like, well, you do read the standard, so let's call it kernel timestamp, and then you actually find this place when you read it in the instruction trace, and it's naturally timestamped, so you do the post-analysis without the extra synchronization, information in the processor trace, because it's needed because it will be naturally timestamped by the hardware itself, and then by starting from that point, you could actually achieve much greater correlation than with the standard solution of reading one timestamp, then another timestamp. You will always get some skew on those. With the instruction trace in place, you could try to invent some magical and crazy schemes to actually work out the timestamp later on. So the process trace opens new possibilities really in this particular case.
But it won't simple.
The other thing that I wanted to mention is that in case when we are dealing with trace coming from multiple machines, physical machines, sometimes it's also useful to think about the networking clock synchronization mechanisms that exist. There's something called IEEE 1588, and that's a standard for synchronizing the network clocks of the different devices on the same network. In the case of our hardware trace that I just talked about, some of the timestamp values that we get in a hardware trace can be sourced from that clock, which is therefore synchronized. It's the network's clock in a sense. So that's one other way to do this correlation across trace data from different physical machines.
So going back to clocks with a variable frequency, I mean, from past experience with older generations of Intel and AMD CPUs that had this kind of behavior, it's quite hard to make sure, to kind of get right the the tracking of those changing, ever-changing clock frequencies, and I mean, there can be a delay between the moment you get a notification, like the event being written, the timestamp of the event that says we're changing the frequency compared to the actual frequency change. And if you have this, that error can accumulate over time, and then you kind of drift compared to your actual real time. So I'm very happy to hear that ARM has a stable clock for tracing purposes. It's very welcome. I really don't know. I mean, what can realistically be done for the variable clock frequency case, but perhaps with a lot of extra analysis overhead. But yeah.
So what can be done is there's a piece of hardware that controls those clock speeds, right? So every time the clock speed has to change, that piece of hardware becomes active. And what can be done is the silicon vendors, they can add a little bit of trace logic to make sure that every time that they intercept those requests for changing the clock speeds, and therefore to have those changes show up in a stream of trace data. So that means that we are going to see the indications that the clock had changed pretty much the moment when that happened.
Yeah, and the same would apply if the clock was being controlled by some kind of control processor on the chip. The OS might be making a request to change clock speed, that then goes to the control processor, which then decides whether or not to change clock speed, or may change it autonomously. And something like CoreSight can capture trace from that processor, non-invasively to the main core. I think the challenge there is to do that in a way which presents the user, the input program, with a set of standard events saying clock speed changed on this core, and abstracting away all the very specific, the stock specific ways in which that's done.
Yeah, from the trace format perspective, I'm trying to see that in a CTF perspective, and well, it could actually be extended so that so currently when in the CTF trace a clock value update field is found, then we basically update the current value of that clock. So then, well, it would be to basically look for frequency change update fields. So whenever they're found in the trace, then we would update the current frequency of the clock. So yeah, these things might be doable.
Well, assuming that we do have the trace data, the hardware trace data contain those indications of clock changes, then the software tool that converts the hardware trace into the CTF format can automatically generate the events with the right timestamps that refer to the same clock.
Other questions in the room? So thank you very much for being at the panel. And well, we'll continue the hallway track, I guess. Thanks.
Thank you.